Hi, everyone. Thank you for joining today's session. Today's topic is Move to Managed Amazon RDS Open Source to Increase Efficiency and Innovation. Quick intros. My name is Sneha Venkateswaran, and I'm a go-to-market specialist for Amazon RDS Open Source and Amazon Aurora here at AWS. In my role, I work with customers every day and answer a lot of questions around how to use RDS, some of the best practices, and some of the benefits around RDS as well. So today, we hope to cover a lot of common questions that do come up to set you up with success using RDS. I'm honored to be joined today by one of our AWS database heroes, Alvaro Hernandez, who's also the CEO of Ongres. Alvaro, do you want to quickly introduce yourself as well?
Yeah, thank you very much for having me today, and thank you everybody for watching this talk. Actually, you pronounce my name very well. That's unusual. Most people say Alvaro, and I'm fine with that. Yeah, absolutely correct, Alvaro Hernandez. So as you said very well, I'm CEO of a company called Ongres. Ongres means on Postgres, and that's pretty much everything we do and a lot of what I do on a daily basis. So I'm working with Postgres all day. I've been doing that for more than 20 years already. And so I'm here to answer any questions about all Postgres and how to do migrations to Postgres. And as you also said very well, I became an Amazon Data Hero 2019. So very happy to be here today.
All right. So quick rundown of today's agenda. We'll go through a quick overview of Amazon RDS. We'll cover some of the key features that can help you innovate and be more efficient. And then we'll go through a demo on migrating self-managed open source databases over to Amazon RDS. And then, of course, we'll wrap with some Q&A. So what is Amazon RDS? Amazon RDS has been around for a while now. It was actually introduced back in 2009 and is one of the earliest services we offered at AWS. We started with MySQL, and since then, we've expanded to several other engines that you see here. And Amazon RDS is a managed relational database service. And what we mean by that is that you can use the database engines that you know and you love, but you have a nice management layer around it to provide you with more automation around common tasks that have typically been mostly manual in nature. And what that brings to the table is an ease of administration. So you don't have to worry about things like provisioning your hardware, patching your database, and maintaining it over time, because AWS takes care of that for you. We also provide some easy capabilities for you to scale your database so that you don't have to over-provision your resources from the beginning. So your resources can grow when your application actually requires it. And as you start to run more production workloads on RDS, we also offer out-of-the-box high scalability and high availability in a very seamless manner that you can enable with just a few clicks. And we also provide all of this in an environment that is highly secure, because security is always number one priority for us at AWS. And with RDS, you're able to leverage things like data encryption at rest and in transit, and also use tools like identity access management to control the access and authentication to your database. So we do offer a wide variety of database engine options on RDS. It ranges from our commercial engines like Oracle and SQL Server that you see on the slide to open source engines like MySQL, MariaDB, and Postgres. We also do have our cloud native engine, Amazon Aurora, that we've redesigned to be optimized for cloud infrastructure. And Amazon Aurora does come in two engine flavors. It's offered with both MySQL and Postgres compatibility. And regardless of what engine you choose on RDS, all of these offer the same managed service benefits that I just walked through. Our focus today is mostly around the RDS open source engine. So we will be focusing more on MySQL, MariaDB, and Postgres. And our demo will specifically be around Postgres as well. Because of the ease of use, high availability, and cost effectiveness, Amazon RDS has hundreds of thousands of customers running production workloads today. You'll see some logos on this slide, and that's just a subset of customers who are using it. And we do have over a decade of expertise to offer in this area to our customers as well. This is probably one of my favorite slides because it provides some nice quantifiable benefits that customers on RDS have experienced when using the service. The numbers here are from an IDC report from last year, which surveyed RDS customers across a wide range of sizes, industries, and geographies. So it is a composite analysis. When customers move to RDS, they do see an overall reduction in TCO because we manage critical administrative functions for you. And so on average, customers have reported seeing a lower total cost of ownership, about 39% over the course of 3 years. And with that, they're also able to get a lot more leverage from their teams to focus on optimizing their application requirements. And that's resulted in about 37% more efficient DBA teams. And with our inbuilt scalability, customers find it about 86% faster to deploy their databases. And if they're thinking about it from a high availability and disaster recovery perspective, customers also see 97% less downtime. So these are pretty compelling numbers. And even if you are a small startup, you can start to leverage these enterprise level availability, reliability, and scalability options right from the start when you're using RDS. So let me quickly touch on a couple of customer success stories using RDS open source. The first one that you see here is Intuit Mint. You may be familiar with Mint as a personal user of it. I do use it myself. It's a personal, free financial management service that displays all of your bank account information and credit card information in a nice little dashboard view, so it can tell you if you're spending too much money. Mint migrated about hundreds of MySQL database instances over from EC2 over to RDS, and that included about 50 terabytes of financial data. And in doing this, they were able to reduce their operational costs by 25%. The other nice benefit that they saw was that they were able to reduce downtime all the way from 30 minutes down to 1 minute. Another favorite case study is Amazon, because what better success story to share than us using the service ourselves? Amazon.com was actually one of the reasons why RDS was born. We saw the operational complexity of managing databases and decided to bring the automation that we built in to other customers as well. This specific case study is actually related to Amazon advertising, which is a little bit more recent from a couple years ago. Amazon advertising moved away from on-premises Oracle to RDS Postgres, and by doing so, they were able to double their throughput. They were also able to double fleet capacity to manage peak traffic. And the other nice benefit that they mentioned was that they were able to take advantage of the RDS console and all of the inbuilt monitoring tools that come with using RDS. They anticipated that if they had to go out and build it themselves, it would have at least been a 3-year project. So some of the key features on RDS, we talked a lot about this, so I won't spend too much time, but Amazon RDS is a fully managed service. And what that means is that we automate a lot of what we like to call the undifferentiated heavy lifting tasks for you. So provisioning databases, patching, scaling, backups, failovers, all of the routine maintenance activities. And by doing that, that frees up time for you to be able to focus on more of the value add activities, like building scalable and resilient applications that will drive your business growth. Once you pick your RDS engine, there are a couple more decisions that you have to make. So first, what instance size are you going to use? And then what storage type do you plan to use as well? And on RDS, the storage and the compute, they both do scale independently. If you look at the compute side first, you're able to scale your compute in 2 main ways. One, you can scale it vertically. So we support all the way up to 96 vCPUs and 768 GB of memory per instance. And then 2, you can also scale horizontally if you want to scale out your reads using read replicas. There are ways to be cost effective with your compute as well. So you can always switch out your instances to be bigger or smaller based on your changing workload requirements at that time. And to be even scrappier with cost savings, there is an option in RDS where you can start and stop your instances. And while an instance is stopped, you don't pay for any compute, you're just paying for the associated storage. So if we flip over to the storage side, you can actually set your storage to auto scale on RDS as well. And this is a huge benefit because you no longer have to worry about pre-provisioning your storage. There is no downtime associated with storage auto scaling, so the change can quickly be made, including reprovisioning IOPS on the fly. We do use underlying EBS storage for RDS, and that can scale all the way up to 64 terabytes. You also have the option on RDS to choose between two different storage types, general purpose and provisioned IOPS. So depending on your workload demands and your IO requirements, you do have that optionality between the two. High availability is something that you can get on commercial databases, but it usually does come at a high price point. On RDS, you can get this right out of the box. RDS offers something called multi-availability zone configuration, and that provides fault tolerance across geographically distant data centers, which is what we call availability zones, or AZs. And these are within the same region, but they're geographically distant. So with a multi-AZ configuration, you get automated failover in the case that there is any type of infrastructure event that happens. The replication between your primary and your standby is synchronous, and it occurs at the block level on EBS, which ensures that there is zero data loss in the case that a failover does occur. Another feature that you might want to take advantage of is the use of read replicas. So on RDS, you're able to create up to 5 read replicas. And one of the primary use cases of read replicas, as the name signifies, is to relieve some pressure off of your source database and offload your reads to the read replica. Another reason to use read replicas is for cross-region purposes. So one, if you're running, say, in US East 1 and you have a cross-region replica in US West 2, you can use US West 2 for lower latency reads if you have customers reading from that specific region. The other use case for cross-region replicas is if you want a disaster recovery, to support a disaster recovery scenario, and there is an issue, say, in US East 1, and you need to promote that read replica in US West 2 to be the new primary. We do get a lot of questions from customers as to when to use multi-AZ versus when to use read replicas, and the use cases are slightly different, and this slide is helpful to walk through exactly what some of those differences are. So the first thing to note that we did talk about, multi-AZ is synchronous, and so it's highly durable in nature to offer and ensure no data loss. Read replicas are asynchronous, so there will be some replication lag between your source and the target. And that's also dependent between the distance of the two. So if it's within the same availability zone, there will be less latency than if it's cross-region, for example. Multi-AZ, only the primary instance is available and active at any given time. The secondary instance is idle, whereas in a read replica, all of the read replicas are available and active for read scalability. In multi-AZ, you can take backups from the secondary instance versus the primary, whereas on using read replicas, you don't really need to take backups because they're read-only copies. You can recreate them at any point in time. With multi-AZs, it's always between 2 AZs within a region. And with read replicas, you have the optionality, depending on your use case, to have them within the same AZ, cross AZs, or even cross-region. Multi-AZ, during database engine version upgrades, both the primary and secondary are upgraded at the same time because they're synchronous. So this does mean that during a multi-AZ configuration, there will be some downtime during these database engine upgrades. Whereas on the other hand, if you're using read replicas, the read replicas are independent database engines, so you can upgrade them independently from the primary instance. And this is actually what we typically recommend. If you're going through version changes, test them on the read replicas first. And then last thing with multi-AZ, you do get automatic failover. So while you can promote a read replica to be a standalone database, this is not automatic. So you would have to go in and manually do it or write a script to get it promoted. In reality, we do see customers that use both multi-AZ and read replicas. They'll use multi-AZ for their production workloads, and then they'll have read replicas off of that multi-AZ configuration. Backups are another feature that are just built into Amazon RDS. We have two main options for backups in RDS. The first one is what you see on the slide here, is automated backups. And this is a window of backups that allow you to do a point-in-time recovery. And a point-in-time recovery is when you may need to rewind your database to a certain point in time. So take an example of maybe yesterday at 4 p.m., you dropped a bunch of tables accidentally, and then you realize that today, what you can do is that you can rewind your database to yesterday around 3:55 p.m. using that point-in-time recovery. And in order to support this, what we do is we take a full automated snapshot of your database every day, and then we store the transaction logs every 5 minutes and ship them off to S3. And so when you restore your database, we take the automated snapshot and then we restore the transaction logs to get your database back to the point that you want it to. And because backups are done by EBS, there's minimal performance impact during these backups. And as I mentioned earlier, if you have a multi-AZ configuration, the backups are actually taken from the secondary EBS volume. You also do have some flexibility with how you set your backup windows, and you can configure your backup retention period to go all the way up to 35 days. The second option available for backups is manual snapshots. So you can do this either using the CLI or an API, take a snapshot of the database, and then store it for use later. RDS snapshots are stored in S3. You can also copy snapshots across regions or across accounts in case you'd like to do that for a more cost-efficient disaster recovery strategy. One thing to note with snapshots is that they are kept forever. So unlike backups, the automated backups, which do have the maximum 35-day retention window, snapshots are available until you choose to delete them. In the interest of time, I'm not going to spend too much time on this slide, but this table just walks through the different options you have available on RDS to configure for both high availability and disaster recovery. And it's really important for you to define what your recovery point objective is, as well as your recovery time objective, and accordingly choose the best HA and DR solution that meets your application's needs. Monitoring. So how do you monitor the health of your RDS database? And we do have several tools, kind of like I had mentioned earlier with the Amazon advertising case study, that are available right out of the box for you to use and are part of our AWS offering. So the first thing that you might be familiar with is CloudWatch metrics. And this provides core metrics like CPU and memory utilization and I/O. You can leverage CloudWatch by also setting alarms. So for example, if CPU utilization goes over 80% for over 2 minutes, you can set an alarm to alert you by setting these predefined thresholds. We also have something called enhanced monitoring for Amazon RDS. And I would encourage everyone to turn that on. And enhanced monitoring gives you some additional metrics beyond what is available on CloudWatch, and it provides it at the host level versus the hypervisor level. The other neat thing that you can do with enhanced monitoring that goes beyond CloudWatch is that you can actually go down to 1 second intervals versus 1 minute. The one thing to note with both CloudWatch and enhanced monitoring is that this is all about monitoring the infrastructure of your database. And that's what brings us to the third tool that we have here on the right, and that's called Performance Insights. Performance Insights looks inside the database to basically see what's going on, what queries are taking up time, what is causing the database to potentially be slow. And using Performance Insights, you can look at the top SQL, and see what SQL statements are causing bottlenecks. And that provides you an ability to analyze and tune your workloads. So this is another feature that I definitely recommend that you turn on and take advantage of as well. To sort of round it out, on RDS, we're continuously innovating, and most of this is based on customer demand. 90% of the new features that we offer is based on direct customer feedback. A nice example of this continued innovation is around our support for Graviton2 instances, where customers were asking us, how can we get better price performance out of the instance types offered? Graviton2 is custom built by AWS using ARM processors, and these processors do provide some better price performance than the predecessor instance types. And these graphs do show that. So the graphs are based on internal benchmarks that compare the performance of M6G Graviton instances on RDS against M5 Intel-based instances on RDS. The way to sort of read this graph, so you on the x-axis, you have the number of threads. On the y-axis, you have the orders per minute. And you can see, as you look at the graph on the left, as we increase the number of threads, you can see that the M5 16x large Intel instance isn't really able to scale much beyond that 60,000 orders per minute. But if you look at the M6G 16x large Graviton instance, it's able to keep going and is able to scale much better. So similar scenario to graph on the right, it's just using a smaller instance size. The one thing to note with Graviton2 instances, it is fully compatible with RDS, and it's just a matter of swapping out your current Intel-based instances with Graviton2 instances. And because of all the testing that we've done, there's no porting, there's no recompilation that's required on your part. It's just a matter of changing your instance type. And so with that, I'm going to hand it off to Alvaro to talk a little bit about how you can actually migrate some of those self-managed databases to one of our RDS open source engines. So over to you, Alvaro.
So thank you very much. I'll take it off from here. And let's see, first of all, which tools are available to migrate self-managed instances or instances managed or in any other environment which is not RDS to Amazon RDS. And we're also going to perform a demo using a self-managed Postgres instance and migrate data to an RDS Postgres instance. So first of all, on the MySQL side, we need to distinguish between both tools that are allowed to migrate from homogeneous environments, so basically MySQL to MySQL or MariaDB to MariaDB, and whether those tools are basically native of MySQL or they're external tools. There's three main mechanisms here. The first one is to restore from a physical backup. So this is a backup you can take with tools like Percona Extra Backup and store them on S3. Then you can restore them from S3 and into RDS, into MySQL RDS. This is an option that works well for databases that are typically large, let's say above 100 gigabytes, because it's going to be more performant than the other options. But it's going to work only for MySQL to MySQL in this case, which is supported by Percona Extra Backup. Then a second option is to use a classical logical mechanism instead of physical, to use the logical mechanism and dump and restore using MySQL dump and MySQL loader, for example. This involves a downtime. You take a dump and then you restore it on the other database, on the RDS MySQL database. And it's optimal in the case where you want to use native tools. In either of these cases, you can announce the process and diminish the downtime by enabling the bin log or using it together with a CDC-based tool. I'm going to also detail more about CDC a bit later in order to diminish this downtime. And finally, you can always use the Amazon DMS, the Database Migration Service, which supports not only continuous migration based on this pattern, CDC, change data capture, but also allows you to migrate across heterogeneous environments. So it could be from MySQL to MariaDB, vice versa, or even other databases to MySQL RDS. So this is about MySQL. About Postgres, the tooling is conceptually similar, except there's no option for migrating from a physical backup or physical streaming replication. I'm going to explain in detail why. So the tools that you have basically available are the first one is a logical dump. It is very used in Postgres, pgdump, pgrestore. However, you're going to be facing downtime here. And because this process may be a little bit slow, depending on the size of the database and all the factors, it might contribute to a long downtime, and it's not usually the preferred option. However, keep in mind that pgdump can be parallelized. And so you can use multiple threads to do the dump in parallel, and then provided that you have enough IO bandwidth, then you might be able to dump fast the data and also restore, obviously, in parallel. A better potentially option, if you're using Postgres 10 at least, is that you use the Postgres built-in logical replication. This is going to be the subject of the demo today, so I'll explain more detail how it works. And finally, you also have, obviously, database migration services. DMS from Amazon allows you to migrate, again, not only from Postgres to Postgres on multiple environments, but also from across multiple different databases from other technologies. So let's dive a little bit deeper today into how to migrate from a non-managed Postgres environment, could be on instance on bare metal, could be another cloud, and then migrate this to Postgres on RDS. So we're going to be looking at using all the options that are available, and in particular, we're going to focus on logical replication. But first of all, let's explain why, in particular for Postgres, we cannot use streaming replication. This may also answer the question that many people may have about why RDS does not allow to configure a replica of another external environment by using streaming replication. So why is not allowed? Well, this is not enabled, and this is a good thing. Even though it may seem like a limitation at some point, it's a good thing. It's all because from a risk factor, databases are obviously parts of the environment where you cannot mess with them. You always need to ensure the data is not only fully durable, but it's also absolutely consistent and is never corrupted. If you use physical replication, in general, physical replication needs to be used with extreme care. For example, physical replication requires that you use the very same Mayer version, Postgres Mayer versions, the CPU architecture, and even the source operating system. So for example, if you wish to migrate a Postgres instance that is running on Intel processors into a new Graviton RDS Postgres instance, with the benefits that Shnia mentioned about Graviton on RDS, you may not be able to do it using a physical streaming replication because Postgres requires that you have also the same CPU architecture. Even more subtly, if the source system may be using a different version of the glibc version, the libc library, it may cause index corruption. This is a subtle problem that you really need to be aware, and it's one of the potential problems you may face by using streaming replication in any environment. You may need to make sure that the collation mechanism supported by both the source glibc implementation and the destination are compatible, which means normally making the versions the same. So this would be quite difficult to migrate across heterogeneous environments into RDS. Also, physical replication is basically byte-by-byte replication. It is logical from the perspective that it comes from the application, but it's physical in the sense that it replicates byte-by-byte, practically speaking. So if there would be any corruption for whatever reason, faulty hardware on the source, that would be propagated also to the destination, making also a potential problem if you would be using streaming replication. And finally, RDS has Postgres supports sections on the pages that form part of the data of the tables, and they are enabled on RDS. Sometimes they're not enabled on source databases, and if you would use a streaming replication, you will not be able to enable them on the fly on these conversions. So these are the main reasons why streaming replication is not available as an option to migrate the data in Postgres land, which also discards using physical backups. So we're limited on one side, but also with the advantages of using logical replication mechanisms in order to migrate data to Postgres and migrate from this self-managed or non-managed instance into Postgres RDS. So how this logical mechanism works? It works mainly by using a principle called change data capture, or CDC. This basically consists on two phases. The first one is a data dump or initial data copy. What it basically does is takes a snapshot of the database, application logical-based snapshot, which is basically a way of keying the database into a state that looks like it's not moving, there's not changing. You're taking a picture, and the database is immutable from your perspective, even though there might be concurrent operations changing the database behind the scenes. Then you do a select, take all the data there and store this data into the destination system. This is the first phase. The second one is the properly streaming of the changes. And it's basically, since the very same time you took the snapshot, the database starts recording the changes that happen to the database, all those inserts or updates or deletes that happen while you're copying this initial data. Then you apply in order these changes on the destination database. And with this, you're able to reconstruct on the destination the same state of the data as it was in the source. So this is basically how change data capture works. The advantage of this mechanism is that it's purely logical, and so it doesn't depend on OS versions, CPU architectures, even Postgres major versions. So you can replicate from any Postgres environment, at least that supports change data capture mechanisms, to a Postgres RDS without any limitation. And there are both built-in mechanisms in Postgres and external tools. Which are those tools? So first of all, there's the idea is based to use logical replication, right? And the main technology for doing this is basically the built-in logical replication that comes with Postgres 10 or greater. If you want to use an earlier version, there's also an extension available on many environments called PG Logical that works since Postgres 9.4 in most environments, in RDS since Postgres 9.6. But anyway, Postgres 9.6 is going to be end of life this year, and you shouldn't be using, my recommendation is not to use a 9.6 as of today as a destination if you're doing a database migration anyway. You could also use external tools like dbsum.io, dbsum in general, which is a great tool for change data capture, very generic. It just requires a Kafka system to have underneath to store the changes and then replicate them, and a Kafka connector. But it's a fantastic tool also for doing this kind of migrations. And obviously, you can use Amazon Database Migration Service, as I just mentioned before, which also supports heterogeneous migrations across different sets of databases. Now, if you use Postgres logical replication, you need to be aware of a few limitations that comes with it. First of all, you cannot do DDL operations. You cannot alter tables and add columns or add restrictions and remove them. But this is something that, as a development team, you can program before doing a production migration, is to stop all DDL changes. You can also not truncate tables, which means empty a given table. These are not big restrictions. You can bear with them in production. Now, some objects are not replicated as part of the logical replication process in Postgres. Sequences, for example, but the workaround is very easy. Just sequence is just a state on the number of the sequence. So yes, when you're going to do the switch over from the old system to the new system, capture the last number and set this number on the sequence and destination. It's something easy to script and automate, and only applies for the sequences you're using. A slightly larger problem is if you use large objects. They are simply not replicated over logical replication. They are not very used today, and normally you can use just byte A fields on regular columns instead of the large object interface, which still provide you up to 1 gigabyte capability of amount of information you can store in a column. It's more or less sufficient for most people, but otherwise there's no workaround. If you use large objects, you need to convert them or migrate them offline. You're taking some downtime for them. You also need a replica identity for every table. And the replica identity is basically a primary key or a index, or create specifically a replica identity which says use the full row in order to support some uniqueness concept on each table, which is necessary for applying the updates and the deletes on the destination. So how do you enable this in Postgres? It's actually relatively simple. On the source system, you need to enable wall level to be set to logical, either minimal or replica, which are the other two values are not valid for using logical replication. And then if you want, this is optional, you can tune a few parameters to control the amount of parallelism. In other words, the amount of threads processes in Postgres sending data either during the initial data copy or during the replication phase. Like, for example, on the source, you configure max wall senders, which is the amount of total replication, both physical and logical, that works in Postgres. Max replication slots, because for logical replication, you're going to be using an underlying technology based on replication slots, and as well, the parameter max worker processes. There are a few relationships between them, and the parameters depends on your I/O storage, the amount of CPUs you have, and so forth. On the RDS destination, the most important parameter is an RDS specific parameter, which is called RDS logical underscore replication, which you need to set to on, is set to off by default, and it's the equivalent of wall level in RDS. And then you can also tune the equivalent parameters on the subscriber side, like the sync workers per subscription, which applies to the number of processes that are going to be capturing the data as part of the initial phase of the CDC, or the logical replication workers, which control the whole pool of processes for the logical replication process. If you need some further tuning guidance in this respect, I recommend you a website called PostgreSQL call.nf, which contains perfect documentation in several languages and recommendations about to use any PostgreSQL configuration parameter. And how would it work? We're going to see right now in the demo, but basically the process is more or less straightforward. On the source, first you can capture the structure of the tables, because on the destination you need to have the same structure of the tables for doing this kind of migration. So you can do a pg dump with only the schema and capture this, and then you will replicate on the destination side. And then just create a publication. Publication is a system which will publish all these changes as well as the initial data to a subscription. Then on RDS side, first we're going to import this schema, where you can do this with PSQL, like replicating the file that we have captured from the pg dump about the table structure. Then we have the same table structure on the destination, and then we create a subscription. Subscription requires a few parameters I will see just during the demo right now. And finally, if you want to monitor the process, you can query a table on the system view on the destination side called pgstat subscription that will give you information about the progress of the migration. So let's jump into the demo. All right, so let's start with the demo. We have a source system, which is a Postgres self-managed instance running on a virtual machine on Google Cloud. And we're going to migrate this instance to Postgres RDS, running obviously on Amazon. So here we have the self-managed instance. It's a regular Postgres. And the first thing we need to do is check the configuration to make sure that we have the wall level and the match workers, as I just mentioned before. So let's just check Postgres configuration and adjust it to enable logical replication. We're going to look for a parameter called wall level. And by default, it's set to replica. We're just going to change it to logical so we can indeed support logical replication. This is the bare minimum that we need to adapt on Postgres land to support logical replication. We could also set different values for the workers that affect the logical replication process. But in this case, we're in general, we're good because the default values that are used for this replication process, they're good enough. We could tune them as I mentioned before, but let's just go with the logical replication for the logical value for the wall level. This change is going to require restart of the database. So in this case, we're just going to need to restart Postgres here. And in this case, we should be good to go if we show the wall level value. Yeah, connection reset because we restart the database. It's now on logical. So this is good enough. Now, the other thing that we need to make sure is that we have a proper connection to allow to Postgres from the external system. So we're going to be connecting, we're going to create a publication on this instance, and then we're going to connect the subscription to this publication from RDS. So we need to allow for this connection. For this, we also need to make sure there's an entry in pghconf file, which controls the income replication connections. In this case, we're going to be using, for simplification purposes, the Postgres user. And we're just going to say, if you look at the last line, that we're allowing connections from the internet in this case, using Scrum authentication mechanism, and we'll allow Postgres connection here for the Postgres user. This operation does not require a restart, so we can do a live reload of the configuration. So this is part of the setup in terms of Postgres configuration. Now, let's look at the database itself. The database has no tables. What we're going to do here is we're going to use a tool called pgbench that we also going to use to run a small benchmark. And while the benchmark is running, we will migrate the data. So let's do a pgbench here. We're going to initialize the data. We're going to set scale the size of around, let's say, 15, and use the database source for this. this will initialize a few tables with a few amount of data, and these are the tables we're going to migrate as part of the database. So if we repeat this, now we have some tables. And we can check the sizes. They're not super big for the purpose of this demo. Now, we need to make sure, if you remember, that all these tables require a primary key. So, or a unique index, or at least we will need to create this replica identity. So if we look at pgbench accounts, this table has a primary key. So here we're good. If we look at branches, it has a primary key also. So we're also good here. If we look at tellers, there's also a primary key. And if we look at history, there's not a primary key. So in this case, we need to create a replica identity. This is a requirement for logical replication. So what I can do is alter table, pgbench history, replica identity full, which means all the whole set of all the row is going to be part of this replica identity. It's going to be a unique concept. This is not ideal. Primary key will be more efficient, but this is how the structure of the table works. So with this, now we need to replicate this table structure on this destination. So what we're going to do here, we don't have any table, obviously. What we're going to do is capture with pgdump. So first of all, I have here just the IPs coded in some variables. So what I'm going to do is we're going to pgdump the schema only, the schema structure of the tables on the source destination. Let's also avoid permissions. And so we're going to connect to the source database. And we're going to look at the database called source. Apologies. Oh, this should dump the schema of the tables here we have. And now we could capture this into a file and just apply to the destination, but actually we can concatenate this on a simple command, on a single command by using pipe. So in this case, let's connect to the destination. It's going to be RDS. Let's connect to the database called RDS. And in this case, I'm using the Postgres user. And this, if all works, should create the table structure the same in the source as the destination. So if we actually go here, good enough, we have the same tables in the source and the destination. Now, the next step, let's go back to the source database, and we're going to create a publication. Create a publication is pretty simple. We can even resort to the help system, but basically, I'll just create a publication. Let's call this migration. And let's say for all tables, I want all the tables to be migrated. You could select the subset, but this is not the purpose of a database migration, right? So I'll just create a publication, and I can list the publication with some shorthand, and here I just have the publication. We're ready to start the migration process. So what I'm going to do right now is I'm going to set up here the pgbench. I'm going to start running a benchmark here. We're going to point to the database called source. That was the name of the database. And we're going to say, let's run this for around 200 seconds, for example. Or yeah, that should be pretty much it. Okay, and here we have the benchmark running. While this benchmark is running is when we're going to start the CDC process, which involves both the copy data part, where we're going to copy the data initially from the source to the destination, as well as the changes that happen within this process. Right now, this process is, this benchmark is not only is changing data, it's inserting rows, it's updating rows. So it's a very good example while this simulates a production workload. So let's go to the destination, and what we're going to do is create a subscription. Create a subscription is also more or less easy process. And in this case, just because I need to remember some parameters, I'm going to get help of the history. And so we're going to create this publication for migration. All passwords are temporary. Don't worry about that. So with this command, we'll just create this subscription. So we don't have, oh, for the user migration. My bad, we said we can use Postgres user here. What happens with demos, and we should be able to create the subscription. In this case, we could look at the tables and they're already replicating. Here we can see that the tables are already getting some changes. We can, as well as I said before, we can list the migrations here. And there's also a view that allows us to monitor the progress of a logical replication, which is a pgstat subscription, where we can see here some parameters about the replication process itself. Now, the good news, as I said, is that this appears to be working right now, and we have some amount of rows here on the process. Let's now wait until the benchmark finishes. And when the benchmark finishes, we'll simulate that we are just cutting off the production traffic, because right now everything is live. We're keep replicating. The process is ongoing here. If we just look at this subscription process, we'll see that there's changes to it. The data is flowing. And when this process will finish, that will be equivalent of, as I said, doing the production cutover. So actually, I'm just going to finish it manually. I'm just going to cancel it. It should be pretty much soon to finish, but we'll just not see the numbers of the benchmark. But that's it. We'll stop the traffic right now. And now we could activate the application on the destination side. Now, to make sure that everything's okay, let's look at, for example, the table. There's one table called pgbench history that was, let's count the rows on pgbench history. This table was initially empty. So now there's 50,000 rows there. Let's check how it is on the destination. Let's stop this. And we have the same number of rows, which already looks pretty good. Let's also look at the pgbench accounts table. This has a field called the balance, which is a numeric value. These are random values. Let's just do a select sum on a balance from pgbench accounts, and find out what is the sum of the balance. This is a number that really tells us nothing here, but it needs to be consistent on both sides. And we can see that it's actually the same number. So this is pretty much what I wanted to show today. Obviously, this is a simplified case. There are some caveats when doing logical replication. But what we've seen here is a process where we took a self-managed instance running Postgres on a virtual machine, and then moved all the tables and all the data to RDS while there was production traffic. So we enabled a benchmark that was constantly changing, inserting, modifying data, and we created a snapshot via the logical replication process as subscription, migrate all the data, all the changes live, and then we just stop the production traffic, in this case, stop the benchmark, and then we can do the cutover. We could have written a tombstone on a table, which is an usual process where you just signal on a source table that you have finished cutting the production traffic, because everything is replicated in order. When this appears on the destination, means that you're ready to go live on the destination. So typically, you can account a downtime of seconds or at most minutes, but never hours or anything like that, regardless of the amount of information.
All right. Thanks, Alvaro. That was an awesome demo. So just quick wrap up here and a call to action for all of you. If you are interested in trying RDS and you don't use it today, we do have a free tier for you to try out. So definitely recommend checking it out if you haven't already. We also have plenty of labs available for you to test and figure out how to spin up a cluster and test out some of the different features that we talked about today, like multi-AZ, for example. And then also you can leverage several of our migration handbooks available in AWS documentation. Alvaro went through a demo today that went through Postgres, but if you have questions around MySQL or MariaDB, we have tons of documentations to help you get started, as well as outlining what the different migration tools and options are that are available to you. If you need more help, feel free to reach out to us, or if you have an AWS account team, please feel free to work with them as well. And with that, we will turn it over to some Q&A and really appreciate the time today. Thanks, everyone.
Thank you, Indy.